So let me back up for just a second. If somebody came up to you that didn't know anything about logarithms and they ask you, what's a logarithm, what would you say without looking at the earlier boards?
An exponent.
Jerome?
It's an exponent.
It's an exponent. Okay? What would be another way of explaining it?
The inverse of the exponential.
Right, you guys are listening. That's great. It's the inverse of an exponential. Okay. Now, let me give you 3 important properties of logarithms without proof. They're not too hard to prove, but I just don't have time here in the class sessions to prove them. There are 3 properties that we have to memorize, and they're kind of similar to your rules involving exponents that you've learned earlier in algebra. One rule is called the product rule. Then there is a quotient rule. And then there is a power rule. I'm going to do it by example. Give me some base.
7.
Base 2? Okay. So if I have a log base 2 of 8 times 49. No, I don't want 49. And I don't want 8. Okay. Actually, the 8 will be okay. Let's make it 64. The product of, the logarithm base 2 of the product 8 times 64. What the product rule is simply, if you ever see the log of a product, it's equal to the sum of the logs. The log of a product equals the sum of the logs. In other words, this becomes the log base 2 of 8 plus the log base 2 of 64. Now, let's answer each of those parts. See in the back row, is that Jada? What's your name?
Yeah,
Jada, yeah. Jada, what's this right here? Log base 2 of 8.
Isn't that what power of 2 gives you 8?
Yes,
So
which would be
3.
3, right on, perfect. So that turns into a 3. What's the exponent of 2 that gives you 8? Answer 3. Good? And what's your name in the back again?
Kyle.
Kyle.
That'd be 6.
6, right on. 2 to the 6th. What's the exponent of 2 that gives you 64? 2 to the 6th is 64. Very nice. So the answer you get for this strange looking thing, which is the logarithm base 2 of whatever that number multiplies up to, that's 480, that's 514 or 512 or something like that. 8 times 64. The log base 2 of that large number is 9. Precisely 9. Example of the product rule. Let's keep. Well, yeah, now you have 3 plus 6. So you do each part and then clean it up. 3 plus 6 gives you 9. Okay, let's look at quotient rule. The log, somebody give me a different base. 7. The log of a quotient, in other words, a ratio. The log of a ratio. Let's do this. Let's make this let's keep it simple, 49 and 7. The log of a ratio is equal to the difference in the logs. So this is going to be the log base 7 of 49 minus the log base 7 of 7. The log of a ratio is equal to the difference in the logs. Taylor, what's this first one? Log base 7 of 49.
9.
Careful. What's the
Oh,
exponent?
7.
What's the exponent of 7? What's the exponent of 7 that gives you 49? Exponent of 7
7.
give you 49. 2.
2.
2. The exponent of 7 that gives you 49 is 2. Over here, Sarah, log base 7 of 7. Exponent of 7 that gives you 7? 1. So we get 2 take away 1 is 1. Can you check that by doing the arithmetic here?
If you really want to.
The log base 7, 7 goes into 49 7 times. What's the log base 7 of 7? 1. Okay. The important thing by the example, though, is that the log of a ratio equals the difference in the logs. The power rule. This is probably the most important rule. If we have something to the power, we're taking a logarithm of something to a power. Let me have another base besides 7 or 2. 3. Let's use five to the 6th power. Log base 3 of 5 to the 6th. They call the power rule. If you're taking the logarithm of something that has an exponent, the exponent pops out in front of the logarithm. This is 6 times the log base 3 of 5. The exponent comes out in front of the logarithm. Exponent comes out in front of the logarithm. Examples of the 3 rules. Okay. Let me grab a problem or two out of the book. And here's something that starts. Everybody have these 3 rules? They're not hard. You just need some practice with them. Max?
With the product rule, what would happen if one of the integers was negative?
Was negative?
Yeah, would it just work out the same
Well,
way?
think of the graph of the logarithms we've drawn. Can the input be negative? Look at the graphs of the logarithms that we've drawn on the other boards here. Can the input be negative? Only if the graph shifted. But if in the fundamental form of a logarithm, can you take the logarithm of a negative value? No, you cannot. The domain is restricted, which means this stuff in here is restricted to positive values. Otherwise, it doesn't make any sense. Okay, good. So we have these 3 rules. What I'd like us to do is to solve a logarithmic equation, similar to what you might see in homework. So let's say we had a problem like, I'll just take one out of the book, and I've got about 5 minutes left is all. In your book, page 89, or number 89 on page 295, it says the log base 2 of 2x plus 1 equals 3. What's the exponent? What's the exponent?
3.
3. See, a logarithm is an exponent, folks. You've got a logarithm equals 3. The exponent is 3. The base is obvious. Base is 2, isn't it? So the way you solve logarithmic equations, try to remember what I'm going to tell you right now. If you ever see an equation involving logarithms, that's what it's called, a logarithmic equation. Pretty obvious. What you do is you isolate the logarithm on one side, similar to what you did with radical equations. You would take and isolate a radical, and then how would you get rid of the radical? you'd square both sides on a radical equation to solve it. Okay, you do something similar here. You isolate the logarithm, and this problem already is isolated, and then you write this in exponent form. Write in exponent form. Remember I said earlier, there's two ways of writing these things. And so what you do, once you've got the logarithm isolated, you know what the exponent is. Happens to be 3. And the base is 2. So 2 to the 3 is equal to 2x plus 1. So you write the equation in exponent form, which is what this says, and then this takes you back to being a linear equation in one variable, beginning algebra. So this is 8 over here on the right, and so you move that over and you get 7, 2x equals 7, x equals 7 halves. Then you always have to check these. Always check log equations, because what happens, folks, is sometimes with logarithmic equations, when you write them in their exponent form, you've now got a new equation. And it's possible to come up with answers that are called extraneous, which will not work. In this case, this will work. So what you can do is put that back into the problem and check it. If you put 7 halves in there, that becomes 7, doesn't it? 7 plus 1 is 8, so the log base 2 of 8, is that equal to 3? What's the exponent of 2 that gives you 8? Yeah, 3 equals 3. Checks. That simple. Okay. See if I can do one more real quick one. How about this one? 102, same page. E to the minus 2x plus 1 equals 13. This is called a, what kind of equation? Don't say logarithm. That's an exponential equation. Very good. Okay, it's an exponential equation. How do you solve exponential equations? You take the logarithm of both sides. You take the log of both sides. What base would be nice to use?
10.
Well, hold it. Look at this. E. Wouldn't base E be nice to use? So take the logarithm both sides. So if I take log base E of e to the minus 2x plus 1 equals log base E of 13, then the power rule lets the exponent pop out in front. Right? Notice these parentheses. Everybody hear that? Notice these parentheses. That comes out in front, and we have log base E of E equals the log base E of 13. What's log base E of E? What's the exponent of E that gives you E? Answer, 1. And so now, log base E of 13 is just a number. It's the exponent of E that gives you 13. It's just a number. And it's available on your calculator. The symbolism for log base E is abbreviated ln, meaning natural logarithm. So we want the natural log of 13. You can punch it on your calculator, and you're going to get a number a little bigger than 2, less than 3. ln of 13, or natural log of 13. And then you're going to solve this thing for x. So what I would do is I'd kick the 2x to the other side, make it positive, and I'd bring the 13, natural log 13, back to this side, and I'd have 1 minus natural log of 13. And then I'd divide by 2 for the exact answer.
Shouldn't that be negative 2?
No, imagine taking the negative 2x over to the other side and bring the 13, natural log of 13 back. I always write the thing I'm looking for on the left, though. Imagine that going over to the other side,
Oh, okay. Got it.
and 1 here, and bring the 13 natural log back to the left, like this. I just wrote it that way. Okay, I had to run a little quick on this. That's the exact answer. You could then turn your calculator on and punch that and get an approximate answer with your calculator. We will spend, in the next class session, we're going to spend quite a bit of time solving exponential and logarithmic equations in more detail. But do you see how handy it is with an exponential equation to solve them? You take the log of both sides, and the power rule lets that exponent pop down in front. That's the key. Okay, that's it for today.